4.5 billion kilometers from the sun, where noon looks like deep twilight and warmth is almost a memory, there is a planet that should be silent. Neptune sits at the far edge of the solar system, so far from its star that the sunlight reaching it is roughly 900 times weaker than what falls on Earth. By every expectation, this world should be frozen, featureless, and still, but it is not. Neptune has the fastest winds ever measured on any planet in the solar system, storms the size of Earth that appear and vanish within years, and an atmosphere locked in constant violent motion. Something is powering this world from within, and tonight you're going to understand exactly what it is and why it matters. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. Neptune was discovered because something was wrong with the math. By the 1830s, astronomers had been tracking Uranus for decades. It had been found in 1781 by William Herschel, the first planet discovered in the age of the telescope, and its orbit had been carefully plotted ever since. But Uranus was not behaving. It was drifting from the path that gravitational calculations said it should follow. The deviations were small but persistent, and they could not be explained by observational error or by the gravitational influence of any known planet. Something massive was pulling on Uranus from beyond, something no one had ever seen. In the 1840s, two mathematicians working independently in different countries set out to calculate where that unseen object had to be. In England, John Couch Adams produced his prediction. In France, Urbain Le Verrier produced his. Their methods differed, but their conclusions pointed to the same region of the sky. On the night of September 23rd, 1846, Johann Galler at the Berlin Observatory pointed his telescope at the coordinates Le Verrier had provided and found a faint blue point of light within 1 degree of the predicted position. It was Neptune, the 8th planet of the solar system, invisible to the naked eye. Too dim and too distant for anyone to have noticed, and without knowing precisely where to look. It was not discovered through exploration or through patient surveying of the heavens. It was discovered through pure mathematics. The gravity of an unseen world had betrayed its presence by tugging on its neighbor, and the equations had done the rest. That mathematical birth is fitting because Neptune has always been a planet understood more through calculation than through direct experience. It is so far away, so faint, so removed from everything familiar that for more than a century after its discovery, almost nothing was known about it beyond the basics. It was big, it was cold, it was blue, and it orbited the sun at a distance so vast that the human mind struggles to hold the number in any meaningful way. Let me try to make that distance real. Neptune orbits the sun at an average distance of approximately 4.5 billion kilometers. That is roughly 30 astronomical units, meaning Neptune is 30 times farther from the sun than Earth is. To say that differently, if you could drive a car at highway speed, 100 kilometers per hour, non-stop, 24 hours a day, 7 days a week, it would take you more than 5,000 years to reach Neptune. 5,000 years. The Egyptian pyramids were built approximately 4,500 years ago. You would not have arrived yet. Light, the fastest thing in the universe, covers the distance from the sun to Earth in about 8 minutes. Sunlight reaches Neptune in roughly 4 hours. When the sunlight currently falling on Neptune's cloud tops left the sun, the morning was still young on this side of the solar system. By the time that light arrives at Neptune, hours have passed. The planet lives in a kind of perpetual time delay from the rest of the system, separated not just by space, but by the time it takes energy to cross that space. Now consider what this distance does to the sunlight itself. Light weakens with distance, not because the photons lose energy as they travel, but because they spread out. Light radiates from the sun in all directions, expanding as an ever larger sphere. The farther you are from the source, the more that sphere has grown, and the more thinly the light is distributed across its surface. The relationship is precise. Double your distance from the sun and the light becomes 4 times weaker. Triple the distance and it becomes 9 times weaker. The intensity falls with the square of the distance. This is the inverse square law, one of the most fundamental relationships in physics, and its consequences for Neptune are extreme. Earth orbits at 1 astronomical unit. Neptune orbits at 30. The square of 30 is 900. That means the sunlight reaching Neptune is approximately 900 times weaker than the sunlight reaching Earth. Think about what that means in practical terms. Stand outside at noon on a clear day on Earth, and the sunlight is blinding, powerful enough to heat the ground, drive winds, evaporate oceans, and power the entire weather system of a planet. Now divide that light by 900. What you are left with at Neptune is not darkness, not quiet, but something close to it. The sun, seen from Neptune, does not dominate the sky. It is still the brightest object visible, brighter than any star, but it is no longer a blazing disk. It's a brilliant point of light, smaller than a pea held at arm's length. Bright enough to cast faint shadows, perhaps. Bright enough to tell day from night. But not bright enough, by any reasonable expectation, to drive powerful weather. And this is where the story of Neptune becomes strange. Because when you understand just how little energy the sun delivers to that distance, you start to build a picture in your mind of what a planet at the edge of the solar system should look like. And that picture is quiet. On Earth, the sun is the engine of everything atmospheric. Solar radiation heats the equator more than the poles. That uneven heating creates temperature differences. Temperature differences create pressure differences. Pressure differences drive wind. Wind carries moisture. Moisture builds clouds. Clouds produce storms. The entire weather system of Earth, every hurricane, every thunderstorm, every breeze, every monsoon, is ultimately powered by solar energy arriving at roughly 1,360 watts per square meter at the top of the atmosphere. That is the solar constant for Earth. It is the budget from which all of our weather is funded. Mars, roughly 1.5 astronomical units from the Sun, receives about 43% of Earth's solar energy. And Mars does have weather. Thin clouds, dust storms, wind. But the weather is weaker, drier, less energetic. The atmosphere is thin and cold. There is less energy to work with, and the result is a planet where weather exists, but struggles. Move farther out. Jupiter, at 5 astronomical units, receives about 4% of Earth's solar input. Saturn, at roughly 9.5 astronomical units, receives about 1%. Both Jupiter and Saturn have spectacular weather systems, enormous storms, banded cloud structures, powerful jet streams, but planetary scientists have long understood that these gas giants are not running on sunlight alone. Jupiter radiates more than twice as much energy as it receives from the sun. Saturn radiates roughly 2.5 times as much. They have internal heat sources, energy left over from their formation, still leaking outward through their thick atmospheres. That internal heat supplements the weak sunlight and helps power their weather. Even so, these are planets relatively close to the Sun compared with Neptune. They still receive meaningful amounts of solar energy. They are big enough and hot enough internally that vigorous atmospheres are expected. But keep going outward, past Saturn, past the gap where the outer solar system begins to thin, past Uranus at roughly 19 astronomical units, where sunlight is about 370 times weaker than on Earth, and then, farther still, to Neptune. At 30 astronomical units, Neptune sits in a region of the solar system where solar energy is almost irrelevant. The sunlight reaching its cloud tops delivers approximately 1.5 watts per square meter. Compare that to Earth's 1,360 watts. Neptune receives roughly 1/900th of what Earth gets. 1/900th. If Earth's entire solar energy budget were represented by a full bathtub of water, Neptune's share would be a few drops. With so little energy arriving from the Sun, what should you expect? You should expect cold. Neptune's effective temperature, the temperature it radiates at, is approximately 59 Kelvin. That is about minus 214 degrees Celsius, or minus 353 degrees Fahrenheit. At these temperatures, most gases we think of as permanent fixtures of an atmosphere would freeze solid. Methane, ammonia, water, all of them condense or freeze in Neptune's upper atmosphere, forming layers of ice clouds deep below the visible cloud tops. You should expect darkness, not complete blackness, because the Sun is still there, still visible, still casting its faint illumination. But a gloom that would feel alien to anything evolved under Earth's bright sky. Noon on Neptune would look something like deep civil twilight on Earth. That brief window after sunset when the sky is dark enough for the first stars to appear, but bright enough that you can still see the ground. Except on Neptune, that twilight never ends. It is permanent, every hour of every day of every century, and you should expect stillness. If the Sun barely delivers enough energy to warm the atmosphere at all, how could it drive powerful winds? How could it build storms? How could it sustain any kind of vigorous atmospheric circulation? The thermodynamic logic is straightforward. Weather requires energy gradients. Energy gradients require an energy source. The Sun is too weak at this distance to serve as a meaningful source. Therefore, the atmosphere should be sluggish at best, frozen at worst, a pale blue sphere of hydrogen and helium and methane sitting in quiet darkness at the edge of the planetary system, doing nothing. This was not an unreasonable expectation. It was the dominant expectation. Before any spacecraft visited Neptune, before we had instruments sensitive enough to study its atmosphere in detail from Earth, the assumption was that Neptune would be a cold, featureless world. A ball of gas and ice with perhaps a few faint cloud bands, some slight variation in colour, maybe a thin haze layer, but nothing dramatic, nothing violent, nothing that would make you sit up and take notice. Uranus reinforced this expectation. When Voyager 2 flew past Uranus in January 1986, 3 years before it reached Neptune, the images were underwhelming by the standards of planetary exploration. Uranus looked nearly featureless, a pale, bluish-green sphere with almost no visible cloud structure, no storms, no banding. It was bland. Scientists described it as the most boring planet in the solar system. And if Uranus, Closer to the Sun than Neptune and receiving more solar energy, was that featureless? Then Neptune should be even more so. Farther from the Sun, less energy, less activity, the gradient pointed clearly toward nothing. There was also a deeper conceptual framework supporting this expectation. Planetary science in the decades before the Voyager missions had developed a general model for how atmospheric activity relates to distance from the Sun. The closer a planet is to its star, the more energy its atmosphere receives, and the more active its weather should be. Venus, closer to the Sun than Earth, has a thick, dynamic atmosphere with super-rotating winds and global cloud cover. Earth has its familiar weather. Mars has diminished weather. The gas giants have weather supplemented by internal heat. But even there, the assumption was that activity would decrease at greater distances. Neptune, at the bottom of this gradient, should represent the minimum, the quiet endpoint, the place where the solar system's atmospheric energy essentially runs out. And if you looked at Neptune through an Earth-based telescope in the 1970s or 80s, nothing would have contradicted this view. The planet was a small, faint blue disk, barely resolved. A few observers had detected hints of brightness variations, possible cloud features, but the data was ambiguous. Neptune was too far away and too small in apparent size for ground-based telescopes to see much detail. It was, in every practical sense, a mystery wrapped in distance, known to be there, known to be blue, known to be cold, but otherwise almost entirely unknown. There is something worth understanding about the state of knowledge before Voyager 2 arrived. We knew Neptune's approximate size, about 49,500 kilometers in diameter, roughly 4 times the width of Earth. We knew its mass, roughly 17 times Earth's mass. We knew its orbital period, approximately 165 Earth years, meaning Neptune had not yet completed a single orbit since its discovery in 1846. We knew its atmosphere contained hydrogen, helium, and methane. The methane was understood to be connected to the planet's blue color, though the precise mechanism belonged to atmospheric physics that would be better understood later. We knew it had at least 2 moons, Triton and Nereid, and we had rough estimates of its temperature. But we did not know what its atmosphere actually looked like up close. We did not know whether it had storms. We did not know how fast its winds blew, if they blew at all. We did not know its internal structure in any detail. We did not know whether it had rings. We did not know how many moons it actually had. We did not know what Triton's surface looked like. Almost everything about Neptune was either a rough estimate or a blank space on the map. And there is a reason for those blank spaces that goes beyond distance alone. Neptune is not just far away. It is visually tiny. Seen from Earth, the planet's apparent diameter is only about 2.3 arcseconds. To put that in perspective, Jupiter's apparent diameter is roughly 20 times larger. Saturn's is roughly 8 times larger. Even Uranus, closer and slightly bigger than Neptune, presents a larger disk. Neptune, through even the best ground-based telescopes of the 1980s, was a smudge. A faint, bluish-green dot that could barely be resolved as a disk at all, let alone studied for surface detail. Astronomers tried, using increasingly sophisticated techniques, including early adaptive optics and speckle imaging. A handful of observers in the 1980s detected subtle brightness variations on Neptune's disk that hinted at possible cloud features, but nothing could be confirmed with certainty as a storm, a band, or a coherent atmospheric structure. The variations were at the very edge of what the instruments could detect. tantalizing but inconclusive. The planet was simply too small in the eyepiece, too far from the telescope, and too faintly illuminated to yield its secrets from a distance of 4.5 billion kilometers. This is the lived reality of Neptune's remoteness. Not just a number. Not just a statistic about how many trillion kilometers separate it from Earth. But the practical, frustrating truth that for more than a century after its discovery, Neptune was a world that could be weighed and measured, but never truly seen. And here is the critical context for everything that follows. When scientists expected Neptune to be quiet, they were not being lazy or unimaginative. They were following the evidence. They were applying the physics, the inverse square law, the thermodynamics of atmospheric heating, the observed gradient from active inner planets to quieter outer ones, the precedent of featureless Uranus. Every line of reasoning pointed toward the same conclusion. Neptune should be cold, dim, and dead. Imagine the solar system as a vast darkening corridor. At one end, closest to the sun, the corridor is bright and warm. Venus and Earth and Mars occupy this space, bathed in strong sunlight, their atmospheres responding to that energy with clouds and winds and storms. As you walk farther down the corridor, the light dims. Jupiter and Saturn are partway down, still illuminated, still active, helped by their own internal furnaces. But by the time you reach the far end of the corridor, the light has faded to almost nothing. There, sitting in the cold and the dark, is Neptune. And everything about the physics of that corridor tells you that this planet at the end should be the quietest room in the building. This is what makes what happened next so important. It is not just that Neptune turned out to be active. It is not just that it had storms or winds. It is that the activity was violent, extreme, among the most powerful atmospheric phenomena ever measured anywhere in the solar system. This was not a modest surprise, not a slight revision of expectations. It was a fundamental contradiction of everything the gradient predicted. Neptune did not cooperate with the physics of diminishing energy. It did something else entirely. And we would not know that until a small robotic spacecraft, carrying cameras and instruments designed in the 1970s, completed a 12-year journey across the outer solar system and turned its lens toward the blue planet at the end of the corridor. Voyager 2 was not built for Neptune. Its primary mission was to visit Jupiter and Saturn, taking advantage of a rare planetary alignment that occurs roughly once every 175 years. The alignment allowed a single spacecraft to use the gravity of each planet to sling itself onward to the next, picking up speed without burning fuel. Jupiter redirected Voyager 2 toward Saturn. Saturn redirected it toward Uranus, and Uranus, after its disappointing grey-green blankness, redirected it toward Neptune. By the time Voyager 2 was approaching Neptune in the summer of 1989, the spacecraft was 12 years old. It had already exceeded its design lifetime. Some of its instruments had degraded. Its cameras were aging. The light at Neptune's distance was so weak that the cameras needed long exposures to capture usable images, which in turn required new techniques to prevent motion blur as the spacecraft flew past. The engineering team at the Jet Propulsion Laboratory spent years developing these techniques, reprogramming the spacecraft from billions of miles away, preparing it for a flyby that would last hours at a target that would fill the camera frame only briefly. Nobody knew what they would see. The working assumption was still that Neptune would be relatively bland, perhaps showing a few more features than Uranus, perhaps not. There was cautious optimism among some atmospheric scientists that Neptune might show signs of activity based on ground-based observations that had detected some brightness variations. But the expectations were modest. The planet was too far from the sun. There was not enough energy. The corridor should be dark and quiet at this end. On August 25th, 1989, Voyager 2 made its closest approach to Neptune, passing within roughly 4,950 kilometers of the planet's cloud tops. It was the closest the spacecraft came to any planet during its entire grand tour, and it was the last planet it would ever visit. The images arrived at Earth about 4 hours after they were taken, traveling at the speed of light across 4.5 billion kilometers of empty space. The signal was faint, the data rate was slow, but when the pictures were assembled and processed, when the team at the Jet Propulsion Laboratory crowded around their monitors and saw what Voyager 2 had found, the quiet planet at the end of the corridor was gone. In its place was something no one had predicted. Neptune was raging, not gently active, not slightly more interesting than Uranus. Raging. The atmosphere was alive with structure. Bands of cloud wrapped the planet in alternating stripes. Bright white features of methane ice streaked across the blue background at enormous speed. And dominating the southern hemisphere, centered near 22 degrees south latitude, was a vast dark oval that the team would name the Great Dark Spot. It was roughly the size of Earth. A vast organized storm, so coherent and so structured that it looked as though it had been raging for years or decades, with clouds racing around its edges at speeds that the instruments measured, and the scientists checked and checked again because the numbers did not seem possible. The wind speeds near the Great Dark Spot were the fastest ever measured on any planet in the solar system. Not by a small margin. By a margin so large that the scientists rechecked the data. Faster than Jupiter's. Faster than Saturn's. Faster than anything Earth has ever produced by an enormous margin. The strongest hurricane winds on Earth reach perhaps 400 kilometers per hour in extreme cases. Neptune's winds were 5 times that. At the edge of the solar system, in the dark, where the sun barely reaches. The cameras also revealed a second, smaller dark spot farther south. Bright companion clouds clung to the edges of the Great Dark Spot. Methane ice crystals lofted to high altitudes by the violent updrafts at the storm's boundary. A fast-moving feature the team called the Scooter raced around the planet in under 16 hours. A bright chevron-shaped cloud moving faster than anything else in the visible atmosphere. The entire planet was a machine of atmospheric motion, with winds at different latitudes blowing in opposite directions, shearing the cloud bands, creating turbulence and structure and violence at every scale the cameras could resolve. Everything about this was wrong. Not wrong in the sense that the observations were faulty. They were checked, confirmed, and consistent across multiple instruments. Wrong in the sense that the physics everyone had relied on said this should not be happening. A planet receiving 1/900 of Earth's solar energy should not have the fastest winds in the solar system. A world sitting in near darkness 4.5 billion kilometers from the sun should not be generating storms the size of Earth. The quiet endpoint of the solar system was not quiet. It was one of the most atmospherically violent places ever observed. And the question that immediately consumed planetary science, the question that still drives research on Neptune's more than 3 decades later, was the simplest and the most difficult question of all. Where is all that energy coming from? The first thing to understand about what Voyager 2 found at Neptune is that you cannot walk on this planet. There is no surface to stand on, no ground, no solid boundary where atmosphere ends and rock begins. Neptune is a world built almost entirely of gas and fluid, and its atmosphere does not sit on top of something the way Earth's does. Instead, it simply becomes denser and hotter the deeper you go, transitioning gradually from thin cold gas at the top to thick, hot compressed fluid far below, without ever crossing a clear line between one state and the other. The visible face of Neptune, the blue sphere that shows up in photographs, is not a surface. It is a layer of cloud and haze floating at a particular altitude in a vast column of atmosphere that extends downward for thousands of kilometers. Everything you see when you look at Neptune is weather. Every feature, every band, every dark spot and bright streak is a structure in the atmosphere itself. There is nothing else to see. The planet is its atmosphere, and its atmosphere is the planet, all the way down until the gas becomes so dense and so hot under the crushing weight above it that it behaves more like a liquid than a gas, and eventually, thousands of kilometers below the clouds, there may be a core of rock and ice roughly the mass of Earth. But that core is buried so deeply that it plays no direct role in anything visible from the outside. What Voyager 2 photographed was the weather layer, the outermost few hundred kilometers of a planetary atmosphere that reaches down into pressures and temperatures no instrument has ever directly measured. The composition of that atmosphere is dominated by hydrogen and helium, the same two elements that make up most of Jupiter and Saturn. Roughly 80% hydrogen, 19% helium, and then the remaining sliver, just 1 to 2%, is methane. That methane is what matters most for what Neptune looks like. Methane molecules absorb red wavelengths of sunlight very efficiently. When white sunlight, containing all visible wavelengths, passes through Neptune's upper atmosphere, the methane strips out the reds and oranges and allows the blues and blue-greens to scatter back toward the observer. This is why Neptune appears blue. Not because it is made of water, not because of any surface feature, simply because a trace gas in the upper atmosphere filters sunlight by color, and what gets reflected back is blue. But Neptune's atmosphere is not just hydrogen, helium, and methane at the top. Below the visible clouds, deeper in the atmosphere where pressure and temperature climb, there are layers that contain water, ammonia, and hydrogen sulfide. These compounds condense into clouds at different altitudes, depending on the local temperature and pressure, creating a layered cloud structure that scientists have modeled but never directly observed. The methane ice clouds are the highest, floating near the top of the atmosphere at low pressures. Below them, predicted but unseen, are layers of hydrogen sulfide clouds, then ammonium hydrosulfide, then deeper still, water clouds at pressures many times greater than Earth's sea level atmosphere. And below even those, the atmosphere continues into regions where the temperature exceeds hundreds of degrees, and the pressure is so extreme that the gas transitions into something dense and exotic, a supercritical fluid that is neither truly gas nor truly liquid. It is in the upper portions of this vast atmospheric column, at the altitudes where methane ice clouds form, and where the temperatures hover near minus 200 degrees Celsius, that Neptune's weather takes place. And the weather is extraordinary. The winds on Neptune move in broad bands that wrap around the planet roughly parallel to the equator. similar in general pattern to the jet streams on Jupiter and Saturn. But there is a critical difference in how those winds are oriented. On Jupiter, the equatorial winds blow in the same direction the planet rotates, what scientists call prograde. On Neptune, the equatorial winds blow in the opposite direction, retrograde, moving against the planet's rotation at enormous speeds. Meanwhile, at higher latitudes, both north and south, the winds shift to prograde, blowing in the direction of rotation. This creates a complex pattern of alternating wind bands, where the atmosphere at different latitudes moves at different speeds, and sometimes in opposite directions. To understand what wind speed means on a giant planet, you need to know what it is measured against. On Earth, wind speed is straightforward. The ground is stationary. Wind is the motion of air relative to the ground. But Neptune has no ground. The atmosphere is the entire planet. So what counts as stationary? The answer is the planet's interior, specifically the rotation of the deep interior, which is inferred from Neptune's magnetic field. A planet's magnetic field is generated by electrical currents deep inside it, and the rotation rate of the magnetic field tells you how fast the core and deep interior are spinning, independent of what the atmosphere above is doing. Voyager 2 measured Neptune's magnetic field and determined that the deep interior rotates once every approximately 16 hours and 6 minutes. This became the reference frame. Wind speed on Neptune is measured as the difference between how fast the atmosphere moves at a given latitude and how fast the interior rotates beneath it. By this measure, the winds near Neptune's equator blow retrograde at roughly 400 meters per second, which is about 1,440 kilometers per hour. That alone would make Neptune one of the windiest places in the solar system. But the fastest winds are not at the equator. They are at higher latitudes, near the edges of the dark spots, where the shear between different wind bands creates the most extreme velocities. Near the Great Dark Spot of 1989, wind speeds exceeded 580 meters per second, more than 2,100 kilometers per hour, roughly 1,300 miles per hour. For comparison, a United States Navy F/A-18 Hornet fighter jet has a top speed of approximately 1,900 kilometers per hour. Neptune's winds blow faster than a military fighter aircraft at full afterburner. The winds are also remarkably stable. Despite the planet's enormous distance from any strong energy source, the wind pattern Voyager 2 measured is not chaotic or fitful. It is organized. The bands persist. The velocities remain roughly constant across the observations. This is not a planet experiencing occasional gusts. It is a planet with a permanent atmospheric circulation of extraordinary power. A global wind machine that operates continuously in near darkness. Now, the Great Dark Spot itself. This was the feature that shocked scientists most because it was not supposed to exist. A planet receiving 1/900th of Earth's solar energy was not expected to produce a storm the size of Earth. But there it was. The Great Dark Spot was an anticyclonic vortex, meaning it was a region of high atmospheric pressure around which winds circulated. On Earth, hurricanes are cyclonic. They are low-pressure systems with winds spiraling inward. The Great Dark Spot was the opposite. A high-pressure system with winds spiraling outward. It rotated counterclockwise in Neptune's southern hemisphere, consistent with the Coriolis effect operating on a high-pressure system in that part of the planet. Its dimensions were roughly 13,000 kilometers by 6,600 kilometers. An ellipse approximately as wide as the Atlantic Ocean and shaped like an enormous dark eye in Neptune's blue atmosphere. The darkness was not absolute. The spot was about 10% darker than the surrounding atmosphere in the wavelengths Voyager 2's cameras measured. It was not a hole in the atmosphere or a shadow. It was a region where the clouds were at a lower altitude than the surrounding areas, allowing the observer to see deeper into the atmosphere, where conditions produce a darker appearance. The most visually striking features associated with the Great Dark Spot were the bright companion clouds that clung to its southern and western edges. These were clouds of methane ice crystals, pushed to high altitudes by powerful updrafts at the storm's boundary. The dynamics were analogous to how air rises over a mountain on Earth, cooling as it ascends and forming clouds on the leeward side. The Great Dark Spot functioned as a kind of atmospheric mountain, an obstruction in the wind flow that forced air upward around its edges, and the methane in that rising air condensed into bright ice crystals at the cold, high altitudes. These companion clouds were among the brightest features Voyager 2 observed, streaking along beside the dark storm like white spray thrown off by a massive wave. The storm also oscillated. Its shape was not fixed. It wobbled, expanding and contracting in a rhythmic pattern with a period of roughly 8 Earth days. This oscillation was consistent with theoretical models of large atmospheric vortices, which predicted that such structures should breathe, pulsing in and out as pressure waves traveled through them. The oscillation confirmed that the Great Dark Spot was a coherent, organized atmospheric structure, not a random patch of disturbed weather. It was a genuine storm system with internal dynamics. Voyager 2 also observed the feature scientists designated Dark Spot 2, a smaller storm farther south in Neptune's atmosphere. Dark Spot 2 had its own distinctive characteristic, a bright core at its center that earned it the informal name Eye. Like the Great Dark Spot, it was an anticyclonic vortex, a high-pressure system with circulating winds, though smaller and less prominent. Its existence told scientists that Neptune was not producing just one large storm as a fluke. The atmosphere was capable of generating multiple vortices simultaneously, suggesting that storm formation was a regular process rather than an isolated event. And then there was the scooter. This was a bright, chevron-shaped cloud feature that moved faster than the Great Dark Spot, lapping it as both features circled the planet. The scooter completed one revolution around Neptune in under 16 hours, matching or even exceeding the rotation rate of the deep interior. Its nature was not fully understood. It may have been a plume of material rising from deeper in the atmosphere, a convective updraft that produced a persistent bright cloud at high altitude. Whatever it was, it demonstrated that Neptune's atmosphere contained multiple independent weather systems moving at different speeds, shearing past one another in a complex dynamic flow. The south polar feature was another bright cloud system observed by Voyager 2 near Neptune's south pole. Unlike the mid-latitude storms, this feature appeared as a persistent bright spot near the pole, possibly associated with atmospheric circulation patterns that concentrate rising air at polar latitudes. It added another piece to a picture that was becoming increasingly clear. Neptune's atmosphere was active at every latitude: equator, mid-latitudes, poles, wind, storms, clouds, convection. The whole planet was in motion, but the atmosphere was not the only thing Voyager 2 revealed. The spacecraft carried a magnetometer, an instrument designed to measure the strength and orientation of a planet's magnetic field. On Earth, the magnetic field is generated deep inside the planet, in the liquid iron outer core, where convective currents of electrically conducting metal act as a dynamo. Earth's magnetic poles sit roughly aligned with the geographic poles, tilted only about 11 degrees from the rotation axis. Jupiter and Saturn show similar alignment. Their magnetic fields are generated in their deep interiors and emerge roughly along the spin axis, as you would expect for a dynamo operating in a rotating body. Neptune broke the pattern completely. Voyager 2 discovered that Neptune's magnetic field is tilted approximately 47 degrees from the planet's rotation axis, not 11 degrees like Earth. Not a modest tilt that could be explained by normal variation. 47 degrees. The magnetic pole is nearly halfway between the geographic pole and the equator. And there is a second anomaly that is equally strange. The center of the magnetic field is not at the center of the planet. It is offset by roughly 0.55 planetary radii, about 13,500 kilometers from the geometric center. The field doesn't emerge symmetrically from the core like the field of a bar magnet, centered in a sphere. It emerges lopsidedly, as if the dynamo generating it is not at the center of the planet at all, but is displaced significantly toward one side. This has profound implications for what is happening inside Neptune. On Earth and Jupiter, the magnetic dynamo operates in a metallic conducting region, at or near the center of the planet. The alignment of the field with the rotation axis reflects the symmetry of the dynamo source. On Neptune, the extreme tilt and offset suggest that the conducting fluid responsible for the field is not a central metallic core. It is a shell, a layer of electrically conductive material at intermediate depth, closer to the surface than the planetary center. This shell is thought to be composed of water, ammonia, and methane compressed under enormous pressure into a state where these molecules become electrically conductive, a hot, dense fluid that can carry the currents needed to sustain a planetary dynamo. The implications ripple outward into everything else Voyager 2 observed. If Neptune's magnetic field is generated in a conductive fluid shell rather than a central core, then the planet's internal structure is fundamentally different from what models based on Jupiter and Saturn would predict. The deep interior is not a simple onion of gas, liquid, and rock. It is something stranger, something whose structure produces a magnetic field that corkscrews wildly through space as the planet rotates. Because the magnetic axis and the rotation axis point in very different directions. Voyager 2 also detected weak auroras on Neptune, glowing patches of atmospheric emission caused by charged particles from the solar wind spiraling along magnetic field lines into the upper atmosphere. But because the field is so tilted and offset, Neptune's auroras do not sit near the geographic poles the way Earth's do. They appear at mid-latitudes, in locations that shift as the planet rotates, adding another layer of strangeness to a world that was refusing to behave like anything scientists had expected. In 2026, observations with the James Webb Space Telescope confirmed the presence of auroral emissions on Neptune in the infrared, providing the first detection since Voyager 2 and revealing that the upper atmosphere had cooled by several hundred degrees since the 1989 flyby, a change that may reflect seasonal shifts or longer-term atmospheric evolution. Neptune's rings were another Voyager 2 revelation. Ground-based astronomers had suspected the existence of rings since the 1980s, based on stellar occultation measurements, observations where a star's light dimmed as Neptune passed in front of it, suggesting something was partially blocking the light. But the occultation data was confusing. Sometimes the dimming appeared on only one side of the planet, not both, which was inconsistent with a complete ring. The explanation turned out to be ring arcs, clumps of material concentrated in portions of a ring rather than distributed evenly all the way around. Voyager 2 confirmed the ring system and revealed its structure. Neptune has 5 principal rings, now named after scientists associated with the planet's discovery and study. The rings are faint and composed mostly of dark, dusty particles, nothing like the bright, icy rings of Saturn. The outermost ring, the Adam's ring, contains the arcs, distinct concentrations of material embedded within the ring. The arcs were named Liberté, Égalité, and Fraternité after the French Revolutionary motto, in honor of the contribution of French astronomers to Neptune's discovery. Why these arcs persist without spreading out evenly along the ring remains an open question. Gravitational interactions with a nearby small moon, Galatea, may help confine the material, but the details are not fully settled. The rings added yet another dimension to Neptune's capacity for surprise. Even its ring system did not behave like a normal ring system. And then there was Triton. Voyager 2's trajectory was carefully designed so that after its closest approach to Neptune, the spacecraft would swing past Triton, Neptune's largest moon, getting within roughly 40,000 kilometers of its surface. Triton is large, about 2,700 kilometers in diameter, and it orbits Neptune in the wrong direction. Every other large moon in the solar system orbits its planet in the same direction the planet rotates. Triton orbits backward, retrograde, circling Neptune in the opposite direction to the planet's spin. This retrograde orbit is strong evidence that Triton did not form alongside Neptune. It was captured. Most likely, Triton was once a Kuiper Belt object, a body orbiting the Sun in the region beyond Neptune, similar in size and composition to Pluto. At some point in the distant past, it wandered too close to Neptune and was seized by the planet's gravity, wrenched out of its solar orbit, and dragged into a retrograde path around the giant planet. That capture would have been a violent event. The tidal forces involved in circularizing Triton's initially chaotic orbits would have released enormous amounts of energy, enough to heat the moon's interior and potentially keep it geologically active for hundreds of millions of years afterward. And when Voyager 2 looked at Triton's surface, it found exactly that. Triton was not a dead, frozen rock. Its surface was geologically young, with very few impact craters, suggesting it had been reshaped recently in geological terms. There were smooth volcanic plains, ridged terrain that scientists compared to the skin of a cantaloupe, and most strikingly, active geysers. Plumes of nitrogen gas and dark dust erupting from beneath the surface, shooting up to 8 kilometers high before being caught by thin winds in Triton's tenuous nitrogen atmosphere and streaking sideways, leaving dark smears on the bright, frozen surface below. Triton was one of only a handful of bodies in the entire solar system where active eruptions have been directly observed, alongside Earth, Jupiter's moon Io, Saturn's moon Enceladus, and possibly Jupiter's moon Europa. And it was doing this at a surface temperature of approximately minus 235 degrees Celsius, one of the coldest measured surfaces in the solar system. The relevance of Triton to Neptune's story is not that the moon explains the planet's atmospheric violence. It does not. But Triton tells us something about the nature of the system Neptune inhabits. Even here, at the edge of the solar system, in the dark and the cold, things are not quiet. The planet rages with atmospheric fury. Its largest moon erupts with geysers of frozen nitrogen. Its magnetic field corkscrews through space at a bizarre angle. Its rings clump into arcs that resist explanation. Nothing about this system behaves the way a cold, distant, quiet corner of the solar system should behave. Neptune and its moons are not the endpoint where activity dies. They are a place where activity takes unfamiliar forms, powered by unfamiliar sources, playing out in conditions that should forbid it. Now, here is what makes Neptune's storms fundamentally different from Jupiter's Great Red Spot, and why that difference matters. Jupiter's Great Red Spot has persisted for at least several hundred years. It was first definitively observed in the 1800s, and some researchers believe it may correspond to a feature described even earlier. It is enormous, about twice the width of Earth, and has been a stable fixture of Jupiter's atmosphere for as long as we have had telescopes capable of seeing it. It changes size and colour over time, but it persists. It endures. Neptune's Great Dark Spot did not endure. When the Hubble Space Telescope observed Neptune in November 1994, just 5 years after Voyager 2's flyby, the Great Dark Spot was gone. Completely. The storm that had dominated Neptune's southern hemisphere, the Earth-sized vortex with the fastest winds in the solar system, had simply vanished. In its place, a few years later, Hubble observed a new dark spot, this time in Neptune's northern hemisphere. That one too would eventually fade and disappear. This pattern has repeated. Over the 3 decades of Hubble observations since Voyager 2's flyby, Neptune has produced multiple dark spots. They appear, persist for a few years, and then dissipate. Based on the observational record, Neptune appears to spend somewhat more than half its time with at least one great dark spot visible. But these are not the same storm persisting. They are different storms, generated by the atmosphere, sustained for a while, and then destroyed. Neptune does not hold its storms, it makes new ones. The most dramatic example came in 2018. The Hubble Space Telescope detected a new dark storm in Neptune's northern hemisphere, roughly 7,000 kilometers across, wide enough that the entire continental United States could fit inside it. Scientists tracked it over the following years, watching it drift southward toward the equator, which is the region where dark spots on Neptune are expected to die. The Coriolis forces that maintain a storm's coherence weaken near the equator, and models predicted that the storm would dissipate once it reached low latitudes. But in August 2020, the storm did something unprecedented. It stopped drifting south, reversed direction, and began moving back toward the north. In 30 years of Hubble observations, no dark storm on Neptune had ever been seen to reverse its drift. The atmospheric dynamics that should have killed it somehow failed, and the storm returned to latitudes where conditions favored its survival. Even more remarkably, Hubble observations from January 2020 revealed a smaller dark spot appearing nearby, roughly 3,900 miles across. Scientists believe this smaller feature may have been a fragment torn from the larger storm, a piece of the vortex that separated and briefly existed as an independent structure before disappearing in subsequent observations. This was a process never previously witnessed. A dark storm reversing course and possibly shedding a fragment. It told scientists that Neptune's atmospheric vortices are more complex and more unpredictable than models had suggested. They do not simply form, drift, and die in a predictable sequence. They interact with their environment. They respond to conditions that we do not yet fully understand. They surprise us. And this connects to a broader truth about Neptune's atmosphere that has become clearer over 3 decades of monitoring. The planet is not experiencing occasional storms against a background of calm. The storms are the background. The atmosphere is perpetually generating vortices, cloud systems, bright features, dark features, activity at all latitudes and all altitudes that the instruments can reach. When one storm dies, conditions are already building another. The wind bands persist regardless of whether a dark spot is visible. The atmospheric circulation is continuous. The violence is structural, built into the way Neptune's atmosphere works, not a temporary disturbance that occasionally interrupts an otherwise quiet system. Consider what this means from the perspective of the expectations that preceded Voyager 2. The prediction was silence. The reality is a planet that produces Earth-sized storms, destroys them within years, and produces new ones. A planet with permanent wind bands blowing at speeds that exceed the capabilities of military aircraft. A planet where bright clouds of methane ice streak across the atmosphere at more than 1,000 kilometers per hour. Where atmospheric features shear past one another as different latitudes rotate at different speeds, where dark vortices the width of continents appear and disappear on timescales that are almost casual by planetary standards. A few years of fury, then gone, then replaced. Neptune's atmosphere is thin by the standards of its enormous depth. The weather layer, the region where clouds form and winds blow and storms rage, is a relatively shallow zone compared with the vast bulk of hydrogen and helium below. But within that thin layer, the activity is relentless. Voyager 2 saw it in 1989. Hubble has tracked it continuously since the mid-1990s. Every time the instruments look, the atmosphere has changed. New clouds have appeared. Old ones have vanished. A dark spot has formed or faded or done something no one expected. There is a detail about how the wind speeds were confirmed that deserves mention, because it illustrates just how extreme Neptune's atmosphere really is. Wind speed on a gas giant is measured by tracking cloud features across successive images and calculating how far they moved in the elapsed time. This technique requires 2 things: identifiable cloud features and precise timing. On Neptune, the methane ice clouds serve as tracers. They're bright enough to stand out against the blue background, and they move with the wind. By measuring the position of a cloud feature in one image and its position in a later image, scientists can calculate the wind speed at that latitude. The reason this matters is that the wind speeds are not theoretical. They are not modeled or inferred from indirect evidence. They are directly measured by watching how fast visible structures in the atmosphere move. When scientists say Neptune's winds reach 2,000 kilometers per hour, they mean they watched a cloud cross Neptune's disk and timed it. The measurement is as direct as watching a leaf blow across a parking lot and timing it with a stopwatch. The leaf is the methane ice cloud. The parking lot is Neptune. And the leaf is moving at 1,300 miles per hour. The implications of what Voyager 2 discovered were immediate and unsettling for atmospheric science. If Neptune, receiving virtually no solar energy, could produce the most powerful winds in the solar system, then the relationship between solar energy input and atmospheric activity was not what scientists had assumed. More energy does not simply mean more weather. Less energy does not simply mean less weather. Something else is at work. Something that can produce extreme atmospheric violence in conditions where the sun is almost irrelevant. And this is the transition that takes us deeper, because identifying the violence is only the first step. The harder question, the one that transforms Neptune from a surprising observation into a genuine mystery, is understanding what powers it. The storms and winds are the symptom. The cause lies somewhere below the cloud tops, in the deep interior of a planet that has been cooling for 4.5 billion years, and has not finished yet. Everything Voyager 2 revealed about Neptune's atmosphere pointed toward an energy source that was not the sun. The winds were too strong, the storms were too large, the activity was too persistent. The solar energy budget was too small by a factor of hundreds. Something inside Neptune was driving the weather, pushing heat upward through the atmosphere, creating the temperature differences and pressure gradients that sustain the wind bands and spawn the vortices. The companion clouds on the Great Dark Spot were a clue. They formed when air was forced upward by the storm's circulation. Upward motion means warm air rising. Warm air rising means heat is being transported from below. The entire storm system was a convective structure, an engine for moving internal heat from the deep atmosphere towards space. The bright methane ice clouds were exhaust, the visible byproduct of a heat engine operating in the dark. The dark spots themselves are windows into this process. They are regions where the cloud deck is depressed, where the observer can see deeper into the atmosphere. The fact that they appear darker means the material at lower altitudes has different optical properties, absorbing more light or reflecting less. But the act of depressing the cloud deck requires energy. Something is pushing the atmosphere downward in those regions while simultaneously creating the high-pressure circulation that defines the vortex. The storms are not just sitting passively in the wind flow. They are dynamically maintained by processes that involve vertical motion, convection, and heat transfer from below. Voyager 2 measured one more thing that confirmed what the atmospheric observations implied. Using its infrared instruments, the spacecraft measured how much thermal energy Neptune was radiating into space and compared it with how much energy Neptune was receiving from the sun. The numbers did not balance. Neptune was radiating significantly more energy than it was absorbing from sunlight. The excess had to come from somewhere inside the planet. This measurement was the key. It turned the observation of violent weather into a physical puzzle with a concrete constraint. Neptune's internal heat was not a speculation. It was a measured quantity. And it was large enough to change the entire energy budget of the planet, making internal heat the dominant driver of atmospheric activity rather than the distant, feeble sun. The storms were real. The winds were measured. The energy imbalance was confirmed. And the question that followed Voyager 2 back across 4.5 billion kilometers of space was the one that planetary scientists have been working to answer ever since. Not whether Neptune is active, that was settled in August 1989, but how a planet so far from its star can sustain such extraordinary violence, using nothing but the heat it has carried inside itself since the day it was born. There is an old principle in physics that says you cannot get something from nothing. Energy is conserved. It does not appear out of nowhere, and it does not vanish into nowhere. It moves. It transforms. It flows from one place to another, changes from one form to another, but the total amount in a closed system stays the same. If you find a system that is outputting more energy than it is receiving, then either your measurement is wrong or there is a source you have not accounted for. Neptune outputs more energy than it receives from the Sun. This is not a subtle imbalance that requires sensitive instruments to detect. It is large, measured first by ground-based infrared observations in the 1970s, and then confirmed by Voyager 2's instruments during the 1989 flyby. The numbers are clear. Neptune radiates approximately 2.61 times as much energy as it absorbs from sunlight. For every unit of solar energy that Neptune takes in, it sends back roughly 2.5 units of thermal radiation into space. The excess, about 1.6 times the absorbed solar power, comes from inside the planet. These measurements were refined and reported by researchers Pearl and Conrath in 1991, using Voyager 2 data, and they have been broadly supported by subsequent observations. A 2025 study published in Geophysical Research Letters, comparing the heat budgets of all 4 giant planets, confirmed that Neptune's internal heat flow remains approximately 162% of the solar power it absorbs. The planet is not in thermal equilibrium with the Sun. It is losing heat from its interior at a rate that dwarfs the faint contribution of sunlight, and it has been doing so for the entire 4.5 billion years since it formed. To understand what this means, think of a stone wall that has spent all day absorbing heat from a fire. When the fire dies down in the evening, the wall continues to radiate warmth into the room. It is not generating new energy. It is releasing energy it stored earlier, slowly surrendering its heat to the cooler air around it. The wall will keep radiating for hours after the fire is gone. If the wall is thick enough and absorbed enough heat during the day, it might still feel warm the next morning. Neptune is doing something similar, but on a scale of billions of years. The fire, in this case, was the process of planetary formation itself. When Neptune formed approximately 4.5 billion years ago, it assembled from a swirling disk of gas, ice, and rock around the young sun. As material fell together under gravity, colliding and compressing, enormous amounts of gravitational potential energy were converted into heat. The forming planet grew hotter as it grew larger. By the time the process was complete, Neptune's deep interior was extremely hot, hundreds or even thousands of degrees, heated by the compression of its own mass. And ever since, that heat has been slowly leaking outward, rising through the layers of hydrogen and helium, through the exotic high-pressure fluids deep inside, through the clouds and haze of the upper atmosphere, and finally radiating into the cold vacuum of space as infrared light. This is primordial heat, not nuclear energy like the fusion reactions that power the sun, not chemical energy, not friction or tidal heating from interactions with moons, though those may contribute a small amount. The dominant source is simply the thermal energy the planet has carried since birth, gradually escaping over geological time. Neptune is still cooling down from the event of its own creation. It has been doing so for the entire age of the solar system, and it has not finished yet. The rate at which a planet loses this stored heat depends on many things: its size, its composition, the efficiency of heat transport through its interior, the thermal conductivity of its layers, whether convection is operating, in which hot material physically rises and cooler material sinks, carrying heat upward far more efficiently than simple conduction through stationary material. In Neptune's case, the internal heat flow is large enough that convection must be a major factor. Heat from the deep interior rises through the planet's fluid layers, reaches the upper atmosphere, and drives the circulation patterns that produce the storms and winds Voyager 2 observed. This is the answer to the question we asked a moment ago. The energy powering Neptune's atmospheric violence does not come from the sun. It comes from below. The sun contributes, but its contribution is the minority share. The majority comes from Neptune's own interior, and it arrives at the weather layer as heat rising from the deep atmosphere, creating temperature contrasts, driving convection, sustaining the wind bands and spawning the vortices. Neptune's weather is powered from the bottom up, not from the top down. And this fact, once you absorb it, changes everything about how you think about the planet. Earth's weather is solar weather. It is the sun's energy, processed through atmosphere and ocean, that produces every storm and every wind on Earth. Take away the sun and Earth's weather dies. Neptune's weather is different. It is internal weather, powered by the planet's own residual heat. Even if you could somehow turn off the sun entirely, Neptune's atmosphere would continue to circulate, continue to produce storms, continue to blow its extraordinary winds, fueled by the heat still rising from 4.5 billion years of slow cooling. Now here is where the story gains a sharp and puzzling edge. Neptune has a near twin. Uranus is almost the same size as Neptune. Its diameter is about 51,000 kilometers, compared to Neptune's 49,500. Its mass is roughly 14 times Earth's, compared to Neptune's 17 times. Its atmosphere has a similar composition: hydrogen, helium, methane. It orbits closer to the Sun than Neptune at about 19 astronomical units, meaning it actually receives more solar energy than Neptune does. By every superficial comparison, Uranus and Neptune should behave similarly. They do not. Uranus has virtually no measurable internal heat. Its energy output is barely above what it receives from the Sun, with a measured ratio of approximately 1.06. Within the uncertainty of the measurements, Uranus might be in perfect thermal equilibrium with its solar input, radiating out almost exactly what it takes in, with essentially nothing coming from inside. This stands in stark contrast to Neptune's ratio of 2.61. Two planets of nearly identical size and composition, one still pouring heat from its interior after 4.5 billion years, the other apparently done. One raging with atmospheric violence, the other comparatively bland. Why? This question has occupied planetary scientists for decades, and there is no single confirmed answer. But there are leading hypotheses. One possibility involves the formation history of each planet. Some models suggest that Uranus may have experienced a giant impact early in its history. A collision with an Earth-sized or larger body that knocked the planet on its side, giving it the extreme axial tilt of nearly 98 degrees that makes it roll around the Sun like a ball rather than spinning upright. This impact could have disrupted the planet's internal structure, mixing its layers in a way that allowed the primordial heat to escape more quickly. If Uranus lost most of its formation heat in the first billion years or so, there would be little left to drive atmospheric activity today. Another possibility, and one that has gained significant support in recent research, involves convective inhibition. Deep inside Uranus, compositional gradients may exist, layers where the mixture of water, ammonia, methane, and hydrogen changes with depth. If these compositional gradients are steep enough, they can suppress convection. Warm material wants to rise. But if the material above it has a different composition that makes it effectively denser despite being cooler, the warm material is trapped. It cannot rise. Heat cannot escape. The planet's interior stays warm, but the heat is locked inside, unable to reach the upper atmosphere and radiate into space. Uranus, by this hypothesis, is not cold inside. It is insulated. Its heat is still there, sealed behind a compositional barrier that prevents it from reaching the surface. Neptune, by contrast, may have avoided this fate. Perhaps its slightly different formation conditions, its greater mass, its different internal mixing history, whatever the cause, allowed convection to operate more freely, creating a pathway for internal heat to reach the atmosphere and escape into space. Neptune's atmosphere gets the benefit of that heat, Uranus's does not. And the result is the dramatic difference in atmospheric activity between the two planets, two nearly identical worlds producing wildly different weather because of what happens thousands of kilometers below their cloud tops. Imagine two houses built from the same materials, the same size, in the same cold climate. One has open vents that allow warm air from the basement to circulate through every room. That house stays warm throughout, with air moving freely from bottom to top. The other house has its vents sealed shut. The basement is just as warm, maybe warmer, but the heat cannot reach the upper floors. The upper floors are cold and still. The warmth is trapped below. Uranus is the sealed house. Neptune is the one with the vents open. Before we go further into how that internal heat becomes weather, it is worth understanding what Neptune is actually made of, because the answer is stranger than most people realize, and it directly affects how heat moves through the planet's interior. Neptune is classified as an ice giant, a term that sounds straightforward but is profoundly misleading. When most people hear the word ice, they picture something solid and cold, a frozen lake, an ice cube, the frost on a winter window. That is not what ice means in planetary science. In this context, ice refers to a group of volatile chemical compounds, primarily water, ammonia, and methane, that are abundant in the outer solar system and were present in the materials from which Neptune formed. These compounds are called ices because they exist as frozen solids in the cold, low-pressure conditions of space. But deep inside Neptune, where pressures reach millions of times the atmospheric pressure at Earth's surface and temperatures climb to thousands of degrees, these compounds are not frozen at all. They are hot, dense, compressed fluids in exotic physical states that do not correspond to anything in everyday experience. The distinction between ice giant and gas giant matters because it describes a fundamentally different kind of planet. Jupiter and Saturn are gas giants. Their bulk is dominated by hydrogen and helium, the lightest elements, compressed into fluid and metallic states at depth. Neptune and Uranus are ice giants. While they have thick outer envelopes of hydrogen and helium, their interiors are dominated by these heavier volatile compounds, water, ammonia, and methane, compressed into a dense, hot mantle that makes up the majority of the planet's mass. This mantle is the medium through which Neptune's internal heat must travel to reach the atmosphere, and its properties determine everything about how efficiently the interior can lose its primordial energy. This is the same conductive layer that Voyager 2's magnetometer revealed indirectly when it detected the planet's tilted, off-center magnetic field. But from the perspective of Neptune's energy budget, what matters about this mantle is not its electrical conductivity, but its thermal behavior. Does it convect freely, carrying warmth upward in rising plumes of hot fluid? Or does it resist, trapping primordial heat below? For Neptune, the evidence points toward effective convection, a mantle that allows internal heat to rise steadily toward the weather layer, feeding the atmospheric violence above. The composition of the planet is not just a detail of internal structure, it is the mechanism connecting the heat source to the weather. And there is one more process that may be occurring in Neptune's deep interior. Something that connects the planet's composition to its energy budget in a way that is both extraordinary and, as of recent years, experimentally confirmed. Deep inside Neptune, at depths of roughly 5,000 miles or more, the pressure exceeds 1 million times Earth's surface atmospheric pressure, and the temperature reaches thousands of degrees. Under these conditions, methane molecules, which consist of one carbon atom bonded to 4 hydrogen atoms, are torn apart. The hydrogen is stripped away, and the freed carbon atoms, subjected to crushing pressure, are compressed into the crystal structure of diamond, solid diamond, forming continuously in the hot, dense interior of the planet, and then sinking downward through the surrounding fluid, falling like rain through thousands of kilometers of compressed water and ammonia toward whatever solid core may exist at the center. This is diamond rain. It sounds like science fiction, but it is grounded in experimental evidence. In 2017, a team led by Dominic Krauss used high-powered lasers at the SLAC National Accelerator Laboratory to compress hydrocarbon plastic, a stand-in for Neptune's methane-rich interior, to the pressures and temperatures found thousands of kilometers below Neptune's cloud tops. Using ultra-fast X-ray pulses lasting just 50 femtoseconds, they observed that nearly every carbon atom in the compressed sample rearranged itself into the crystal structure of diamond. The nanodiamonds that formed were tiny, just a few nanometers across, but their crystalline structure was unambiguous. Diamond had formed under Neptune-like conditions in a laboratory on Earth. Subsequent experiments in 2020 and 2022 refined the results, using plastics that contained oxygen alongside carbon and hydrogen to more closely approximate the actual chemical mixture inside Neptune, which includes water and ammonia as well as methane. The diamond formation persisted under these more realistic conditions. And in January 2024, a follow-up study published in Nature Astronomy, led by Mungo Frost, produced a particularly significant finding. Diamond formation occurred at substantially lower pressures and temperatures than the earlier experiments had suggested. This means that diamonds likely form over a much larger region of Neptune's interior than originally calculated, beginning at shallower depths and extending over a thicker shell of the planet's mantle. The implications are twofold. First, as diamonds form and sink, they release gravitational energy. A dense object falling through a less dense fluid converts potential energy into heat. The same principle that makes a meteorite glow as it falls through Earth's atmosphere, though the mechanism inside Neptune is frictional drag rather than atmospheric compression. This means diamond rain could be an additional source of internal heat, supplementing the primordial energy from formation. Every diamond that forms and falls deposits a small amount of energy into the surrounding fluid. Over 4.5 billion years, across an entire planetary interior, the cumulative contribution may be significant. It may help explain why Neptune is still so warm, still radiating so much more energy than it receives from the sun. Second, as the diamonds sink through the mantle, They stir the electrically conductive fluid around them, disrupting convective patterns and potentially affecting the dynamo that generates Neptune's magnetic field. The 2024 study explicitly linked diamond rain to the unusual magnetic fields of both Neptune and Uranus, suggesting that the distortion caused by sinking diamonds could help explain why the fields are so tilted and offset compared with the orderly, symmetric fields of Earth and Jupiter. The internal structure of Neptune, the exotic compressed fluids, the diamond formation, the disrupted convection, all of it feeds back into the properties we observe from the outside. The strange magnetic field, the excess heat, and ultimately the violent atmosphere. What Neptune's deep interior actually looks like in full detail remains unknown. No instrument has ever directly probed it. Everything we know about the conditions thousands of kilometers below the cloud tops is inferred from models, from laboratory experiments, from the magnetic field measurements Voyager 2 made during a few hours in 1989, and from the thermal energy the planet radiates into space. But the picture that emerges from these fragments is consistent and remarkable. Neptune is not a simple ball of cold gas. It is a layered, complex world with an interior dominated by compressed volatile fluids in exotic states, where carbon is crushed into diamonds that fall like slow rain through a hot, dense, electrically conductive ocean, releasing energy as they go, stirring the fluid that generates a magnetic field unlike anything in the inner solar system. This is the engine below. Not just residual heat from formation, though that is the dominant source, not just convection carrying warmth upward, though that is the primary transport mechanism, but a deep interior where the very composition of the planet participates in the energy budget, where exotic chemistry under extreme pressure creates processes that have no analog on any world closer to the Sun. Understanding that Neptune's weather is driven by internal heat resolves the paradox of a violent atmosphere in near darkness, but it opens a new set of questions about how the atmosphere actually converts that rising heat into the specific phenomena we observe. The process is not as simple as hot air going up and cold air going down. The atmosphere is a rotating fluid on a rapidly spinning planet. Neptune completes one rotation in roughly 16 hours. That fast rotation imposes strong Coriolis forces on any moving parcel of air, deflecting it sideways rather than allowing it to move straight from pole to equator. The result is that atmospheric circulation on Neptune is organized into zonal bands, east-west flows that wrap around the planet, rather than the single-cell convective pattern you might naively expect. The interaction between rising internal heat and the planet's rotation creates the banded wind structure. Warm material rises in certain latitude bands, creating zones of upwelling. It cools, spreads horizontally, and sinks in adjacent bands, creating zones of downwelling. The Coriolis force turns these vertical motions into horizontal jets, alternating bands of prograde and retrograde wind that circle the planet at different speeds. The result is the pattern Voyager 2 observed. Organized, persistent, powerful wind bands maintained not by the sun, but by the continuous upward flow of heat from below. There is another factor that helps explain why Neptune's winds are so fast, despite its relatively modest energy budget compared to Jupiter or Saturn. Friction. On Earth, wind is slowed by contact with the surface. Mountains, forests, oceans, buildings, all of these create drag that extracts energy from the wind and slows it down. Even the ocean surface, smooth as it appears, creates friction that limits wind speed. On Neptune, there is no surface. The atmosphere transitions smoothly into denser and denser fluid below, without a sharp boundary. There's nothing to slow the wind. Once a jet stream forms, the only things that can decelerate it are interactions with other atmospheric flows and the slow loss of energy through radiation. Both of these processes are weak compared to surface friction on a rocky planet. The result is that even a modest energy input can sustain very high wind speeds, because there is so little working to slow them down. Neptune's winds are not necessarily the product of enormous energy. They may be the product of enormous efficiency, a system where almost nothing resists the motion once it starts. This combination of internal heat driving convection, fast rotation organizing that convection into zonal bands, and negligible surface friction allowing wind speeds to build unchecked, is the current best explanation for Neptune's atmospheric violence. It is not a complete explanation. Models still struggle to reproduce the exact wind profile that Voyager 2 measured. The details of how heat moves through Neptune's deep interior and enters the weather layer are not fully understood. The role of moist convection, where water or ammonia or methane condenses and releases latent heat, adding energy to rising air parcels, is still being investigated. But the broad picture is clear. Neptune's atmosphere is a heat engine running on primordial energy, organized by rotation and largely unbraked by friction. That is why the winds blow at 2,000 kilometers per hour in a place where the sun barely shines. But the sun is not entirely absent from the story, and this is one of the most surprising discoveries of the last few years. In 2023, a research team led by Erandi Chavez and Imku de Pater at the University of California, Berkeley, published a study in the journal Icarus that analyzed nearly 30 years of Neptune observations from the Keck Observatory in Hawaii and the Hubble Space Telescope, supplemented by data from the Lick Observatory in California. They had tracked the appearance and disappearance of Neptune's clouds from 1994 through 2022. What they found was unexpected. Starting in late 2019, Neptune's mid-latitude clouds almost entirely vanished. The bright features that had been a consistent part of Neptune's appearance for decades, clouds of methane ice at various latitudes, simply faded away. By 2022, the planet was nearly cloud-free except for a persistent feature near the South Pole. This was the most dramatic and prolonged disappearance of clouds in the entire observational record. When the team looked at the full 30-year dataset, a pattern emerged. Neptune's cloud abundance waxed and waned in a cycle that correlated with the sun's 11-year activity cycle. When the sun was more active, producing more ultraviolet radiation, Neptune tended to develop more clouds, with a lag of approximately 2 years. When solar activity declined, Neptune's clouds faded, again with a delay. The 2019 disappearance corresponded to the deep solar minimum at the end of solar cycle 24, and the correlation across 2.5 complete solar cycles was statistically compelling. This was a surprise because Neptune receives so little solar energy, only about 0.1% of what Earth gets, that the sun's influence on Neptune's weather seemed negligible. But what the data showed was not a direct heating effect. It was photochemistry. The sun's ultraviolet output, which varies much more strongly than its visible light over the solar cycle, triggers chemical reactions high in Neptune's atmosphere. These reactions produce haze particles that may serve as seeds for cloud formation. When ultraviolet levels are high, more seeds form, more clouds develop. When ultraviolet levels drop, fewer seeds form, fewer clouds appear. The process takes about 2 years to percolate through the atmosphere, explaining the time lag. So Neptune's clouds are partly controlled by the sun after all, not through direct heating, but through a subtle photochemical pathway that links the sun's magnetic activity to ice crystal formation in a planet's atmosphere 4.5 billion kilometers away. The sun does not power Neptune's winds. It does not drive Neptune's storms, but it modulates the visible weather, adjusting the amount of cloud cover through a chain of chemical reactions that begins with ultraviolet photons and ends with methane ice crystals. In July 2022, the James Webb Space Telescope turned its near-infrared camera toward Neptune and captured the clearest images of the planet since Voyager 2. Because the telescope operates in infrared wavelengths, Neptune appeared strikingly different from its familiar blue portrait. Methane absorbs strongly in the near-infrared, so the planet appeared mostly dark, with bright patches where high-altitude methane ice clouds reflected sunlight before the methane below could absorb it. The images revealed Neptune's rings with a clarity not seen in more than 30 years, including the faint inner rings that had been nearly invisible in Voyager 2's data. But the most scientifically interesting feature was a thin, bright band encircling Neptune's equator. This was not a cloud band in the traditional sense. It was a signature of warmer gas, possibly a zone where atmospheric circulation brings material downward from higher altitudes, compressing and warming it. This equatorial feature is thought to be a visible trace of the global atmospheric circulation that drives Neptune's weather. The large-scale pattern of rising and sinking air that transports internal heat from the deep atmosphere towards space. If confirmed, it would be a direct observation of the engine that powers Neptune's winds. The meridional circulation that connects the heat source below to the weather layer above. The James Webb data also revealed details about cloud structures at different atmospheric levels. By selecting infrared wavelengths where methane absorption is weaker or stronger, the telescope could peer to different depths in the atmosphere, building a three-dimensional picture of cloud structures that ground-based telescopes and even Hubble could not match. Bright features in the southern hemisphere showed up as high-altitude methane ice clouds, consistent with the companion clouds Voyager 2 had observed near the Great Dark Spot, though no large dark spot was present at the time. There is one more discovery from recent years that belongs here because it corrects a misconception about Neptune that has endured for decades. In January 2024, a study led by Professor Patrick Irwin of the University of Oxford, published in the monthly Notices of the Royal Astronomical Society, demonstrated that Neptune's famous deep blue colour is not real. Or more precisely, it is not what Neptune actually looks like to the human eye. The images released after Voyager 2's flyby in 1989 were processed with enhanced contrast to make atmospheric features visible. The science team deliberately stretched the colour and brightness to reveal cloud bands, storm structures, and subtle variations that would have been difficult to see in a true colour rendering. This was a standard practice and scientifically justified. The enhanced images were released with captions explaining the processing, but over time, the distinction was lost. The deep azure Neptune became the planet's public identity, reproduced in textbooks, documentaries, posters, and websites for 35 years. Irwin's team used calibrated spectrograph data from the Hubble Space Telescope and the European Southern Observatory's very large telescope to reprocess the original Voyager 2 images with accurate color balance. The result was striking. Neptune is not deep blue. It is a pale greenish blue, remarkably similar to Uranus. The two ice giants, so different in atmospheric activity, are nearly identical in color. The visual difference that had lodged itself in public consciousness was an artifact of image processing, not a physical property of the planet. This matters because it strips away one more layer of illusion. For decades, Neptune's dramatic blue color reinforced a visual impression of drama, of something exotic and intense about the planet's appearance. But Neptune's true face is muted, gentle, almost serene, a soft blue-green sphere hanging in the darkness, looking for all the world like a planet at peace. And that is the deepest deception Neptune offers. Its appearance lies. The surface that faces the universe is calm, pale, and quiet. But beneath that calm surface, the atmosphere is moving at speeds that exceed the speed of sound on Earth. Storms the size of continents form and dissolve in cycles measured in years. Wind bands powered by internal heat circulate the planet continuously. And the engine driving all of it has been running since the formation of the solar system itself, slowly releasing the heat that Neptune has carried in its core for 4.5 billion years, with no sign of stopping. The sun contributes a little. It adjusts the cloud cover through photochemistry. It provides the faint illumination that makes the planet visible at all. But the fundamental energy that powers Neptune's atmospheric fury is not solar. It is planetary. It belongs to Neptune itself, a remnant of the violence of formation, still working its way outward through layers of gas and fluid and ice, still driving convection, still sustaining the fastest winds in the solar system long after the planet was supposed to have cooled into silence. Neptune has not cooled into silence. It has not stopped. It is not winding down in any way that matters on human timescales. The heat will continue to escape for billions of years to come, gradually diminishing, slowly letting the atmosphere settle. But that settling is so far in the future that it is meaningless for anyone who will ever observe this planet. For now, and for any foreseeable now, Neptune is still running. The engine below is still turning, and the atmosphere above is still raging in the dark. What remains is to step back and look at what all of this means, not just for Neptune, but for how we understand the outer solar system and the worlds that populate its cold, dim reaches. Because Neptune is not just an interesting anomaly, it is a correction. A revision of a story we thought we understood about what happens at the edge of a planetary system, where sunlight fails and darkness takes over. Neptune proves that the story is wrong. And the real version is more complicated, more violent, and far more interesting than anyone expected. There is something Neptune does that no photograph can capture, and no single observation can reveal. It changes. Not in the way a spinning top changes, repeating the same motion endlessly. It changes in the way a living system changes, responding to conditions, producing new structures, destroying old ones, shifting its appearance across years and decades in patterns that are only now beginning to come into focus. Neptune takes approximately 165 Earth years to complete a single orbit around the Sun. That means a full Neptunian year is longer than the entire period since the planet was discovered. Neptune did not finish its first complete orbit since Johann Galle first saw it in 1846 until approximately 2011. Even now, it has barely completed more than a single trip around the Sun in the entire time humanity has known it exists. And because Neptune's axis is tilted at roughly 28 degrees, similar to Earth's tilt, the planet experiences seasons. But each season on Neptune lasts about 40 Earth years. When Voyager 2 arrived in August 1989, Neptune was in its late southern spring, approaching summer. The South Pole was tilted toward the Sun, receiving slightly more of the already faint sunlight. The Great Dark Spot sat in the southern hemisphere. The South Polar Feature glowed brightly near the pole. The atmospheric activity Voyager 2 observed was a snapshot of one season in one hemisphere at one moment in a year that stretches across nearly 2 centuries. Since then, Neptune has moved forward in its orbit. The seasons have shifted. The planet is now approaching a different seasonal configuration than the one Voyager 2 witnessed, and the atmosphere has responded. Ground-based telescopes and the Hubble Space Telescope have tracked changes in Neptune's cloud patterns over 3 decades. Cloud activity has migrated between hemispheres. Bright features that were concentrated in the south during the Voyager era have appeared in the north. The dark spots have moved from the southern hemisphere to the northern hemisphere. The overall brightness of the planet at certain wavelengths has varied, suggesting shifts in atmospheric haze and cloud altitude. These seasonal changes are remarkable because they demonstrate that Neptune is not merely active, it is responsive. Its atmosphere adjusts to changing conditions over timescales of decades. The Sun may be faint at Neptune's distance, but the slight variation in how sunlight falls on different hemispheres as the planet orbits is enough to modulate the distribution of atmospheric features. The internal heat provides the energy. The seasons help shape whether energy manifests as visible weather. But here is the sobering reality. Everything we know about Neptune's atmospheric changes since 1989 comes from telescopes that are billions of kilometers away. No spacecraft has returned. No probe has dropped into Neptune's atmosphere. No orbiter has circled the planet to study it from close range over months or years. Voyager 2's flyby lasted hours. It captured one set of images, one set of measurements, one brief window into a planet that changes on timescales of years and decades. Everything since has been inferred from the light that reaches us across the solar system, filtered through Earth's atmosphere when observed from the ground, or captured by orbital telescopes that were designed for many purposes, not primarily for staring at Neptune. This means our understanding of Neptune is built on an extraordinarily thin foundation. We have one close encounter from 1989 and 3 decades of distant monitoring. Imagine trying to understand Earth's climate system from a single airplane flyover, and then watching from a satellite so far away that individual continents are barely resolved. You would see broad patterns. You would detect changes in cloud cover. You would measure temperature variations. But you would miss almost every lag that actually matters for understanding how the system works. The details, the mechanisms, the interactions between layers, all of that would be hidden beneath the limits of your instruments. Neptune is in that situation. We know the atmosphere is violent. We know internal heat drives it. We know the winds are extraordinary. We know storms form and dissipate and sometimes behave in ways that surprise us. But we do not know why the winds have the specific speeds they do at specific latitudes. We do not know how heat moves through the deep interior and enters the weather layer. We do not know what triggers the formation of a dark spot in one decade but not another. We do not know the detailed composition of the atmosphere below the cloud tops. We do not know the structure of the interior, whether there is a distinct core or a gradual transition, whether the exotic high-pressure materials deep inside behave the way our laboratory experiments suggest, or in ways we have not anticipated. Planetary scientists have proposed dedicated missions to address these gaps. The most prominent concept in recent years is the Neptune Odyssey, a mission study developed for NASA's Planetary Science Decadal Survey. The concept envisions an orbiter that would spend years circling Neptune, studying its atmosphere, magnetic field, rings, and moons in detail, paired with a probe that would descend into the atmosphere and measure composition, temperature, pressure, and wind speed directly as it dropped through the cloud layers. Such a mission would transform our understanding of Neptune the way the Cassini mission transformed our understanding of Saturn. It would turn Neptune from a planet known through brief glimpses and distant observations into a planet known through sustained, close-range study. But no Neptune mission has been approved. The distances involved are daunting. A spacecraft traveling to Neptune would need roughly 12 to 16 years just to get there, depending on the trajectory and available gravity assists. The mission would require a power source that works far from the sun, almost certainly a nuclear generator, since solar panels are inadequate at 30 astronomical units. The communication delays would be significant, with signals taking more than 4 hours each way. And the cost would be substantial, competing with other scientific priorities for limited funding. This means Neptune will likely remain the least visited and least understood major planet in the solar system for years, possibly decades, to come. Every new observation from Hubble or the James Webb Space Telescope adds something. Every ground-based campaign from Keck or Gemini or the Very Large Telescope contributes a data point. But the fundamental limitation remains. We are studying a dynamic, complex, violent world from a distance of 4.5 billion kilometers, and we have been inside its system exactly once, for a few hours, more than 36 years ago. What makes this gap in knowledge more than just a scientific inconvenience is what Neptune represents in the broader context of planetary science. Because Neptune is not just one planet. It is the archetype for an entire class of worlds that we are now discovering throughout the galaxy. Over the past 2 decades, planet hunting missions and ground-based surveys have revealed that Neptune-sized planets are among the most common types of worlds in the Milky Way. The Kepler Space Telescope, which surveyed a patch of sky for transiting exoplanets, found that planets between the size of Earth and Neptune are extraordinarily abundant. Many of these worlds, called sub-Neptunes or mini-Neptunes depending on their size, orbit other stars at distances where their atmospheres may be thick, hydrogen-rich, and potentially similar in character to what we see on Neptune and Uranus. These are the most common type of planet discovered so far, and they have no analog in the inner solar system. The closest analog we have is sitting at the edge of our own system, largely unstudied, poorly understood, visited once for a few hours in 1989. Understanding Neptune's atmosphere, its internal heat, its weather dynamics, its energy budget, is not just about one planet. It is about building the physical framework we need to interpret observations of hundreds or thousands of similar worlds around other stars. When the James Webb Space Telescope measures the atmospheric composition of a sub-Neptune exoplanet, the models used to interpret that measurement are informed by what we know about Neptune and Uranus. When astronomers try to understand whether a distant Neptune-sized world has active weather, they draw on the physics of atmospheric circulation that we have tested, imperfectly, against our own ice giants. If our understanding of Neptune is incomplete, then our understanding of all Neptune-like worlds is incomplete. And since Neptune-like worlds may be the most common type of planet in the universe, the stakes of that incompleteness are enormous. Neptune is not an obscure curiosity at the margin of our solar system. It is the template for an entire category of planet that populates the galaxy. And we barely know it. This brings us to the larger question that Neptune forces us to confront, and it is a question that goes beyond the mechanics of atmospheric physics. What did we get wrong about the outer solar system? And what does that error tell us about how we think? For most of the history of planetary science, the outer solar system was treated as a region of diminishing interest. The closer a planet is to the Sun, the more energy it receives, the more active it should be, the more scientifically interesting it ought to be. This gradient of relevance placed Mercury, Venus, Earth, and Mars at the center of attention. Jupiter and Saturn, being spectacular and relatively close, received the next tier of interest. Uranus and Neptune, dim and distant, were the afterthoughts. They would be visited eventually, studied when convenient, but they were not where the action was. The action was closer to the Sun, where the energy was, where the drama was, where the science seemed richest. Neptune destroyed that assumption. It showed that a planet does not need the Sun to be violent. It does not need proximity to a star to sustain an active, dynamic atmosphere. It does not need to be close to the center of a system to be one of the most extreme environments in that system. The gradient of relevance was wrong. The outer solar system is not a region of diminishing activity. It is a region of different activity, powered by different sources, operating under different rules, but no less real and no less extreme. This correction matters because it changes what we expect when we look at planetary systems around other stars. If distance from a star meant silence, then the outer regions of other planetary systems would be uninteresting. Just cold rocks and frozen gas drifting in darkness. But Neptune tells us that distance from a star does not mean silence. It means something else. It means that whatever activity exists is self-powered, running on internal energy rather than stellar energy, potentially sustained for billions of years without any help from the star at all. A Neptune-like planet orbiting a dim red dwarf star in a wide orbit, receiving almost no stellar energy, could still have a violent atmosphere. A rogue planet drifting through interstellar space with no star at all, if it were massive enough and had retained enough primordial heat, could still have weather. The concept of a habitable zone, the region around a star where conditions might be right for liquid water, is defined by stellar energy. But Neptune suggests that stellar energy is not the only game. Internal heat can drive atmospheric dynamics in places where no star shines. The possibilities for what a planet can do in the dark are far richer than anyone imagined before Voyager 2 arrived at Neptune. And now we arrive at the core of what makes Neptune not just scientifically significant, but genuinely unsettling to contemplate. It is the contradiction. Neptune should be quiet. Every line of reasoning that begins with its distance from the Sun, with the inverse square law, with the thermodynamics of atmospheric heating, ends at the same conclusion. This planet should be a frozen, featureless sphere drifting in darkness at the edge of the solar system. It should be the place where the Sun's influence effectively ends and everything settles into cold, permanent stillness. It should be boring. It should be dead. But it is not dead. It is not still. It is not even close to still. It is one of the most atmospherically extreme worlds in the entire solar system. Winds that would shred any structure built by human hands. Storms that span the width of continents and appear and vanish on timescales that suggest the atmosphere treats them almost as routine. A global circulation that runs continuously, driven by heat rising from an interior that has been cooling for 4.5 billion years and still has not cooled enough to stop. A planet that radiates more than 2.5 times the energy it receives from its star, not because of any exotic process, but simply because it has not yet finished losing the heat it was born with. The contradiction is what makes Neptune terrifying. Not terrifying in the way a volcano is terrifying, with immediate obvious danger. Terrifying in the way that a fundamental surprise is terrifying. The realization that the universe does not work the way you assumed. You looked at the edge of the solar system and expected peace. You found violence. You expected silence. You found a roar. You expected a planet that had surrendered to the cold and the dark. You found one that refuses. There is a tendency, when discussing the planets, to rank them by proximity to human experience. Mars feels almost familiar, with its rocky deserts and thin sky. Jupiter feels dramatic and powerful, a monster of gas and gravity. Saturn feels elegant, ringed, and luminous. Neptune feels remote, irrelevant, a world so far away and so cold and so dark that it has nothing to do with anything that matters to human life. But remoteness is not irrelevance. Neptune's atmospheric physics, the interplay of internal heat and rotation and composition that produces its weather, operates under the same laws that govern every atmosphere in the universe. The same thermodynamics, the same fluid dynamics, the same conservation laws. Understanding why Neptune rages is understanding something general about how planets work, not just how one peculiar blue world at the edge of our system behaves, but how energy and matter and motion interact in thick atmospheres under conditions of low external energy input. This is physics that applies to worlds we will never visit, around stars we will never reach, in regions of the galaxy we can only observe through telescopes. Neptune is a laboratory for understanding those worlds, and it is the only one we have. And there is something else, something harder to articulate but worth trying to say. Neptune forces a correction in how we think about what matters at the margins. In science, as in life, there is a bias toward the center. The brightest, the closest, the most energetic, the most obviously dramatic, these are the things that attract attention. The margins are quiet. The margins are where things run down. The margins are where you stop looking because there is nothing left to see. Neptune says otherwise. Neptune says that the margins can rage. That distance from the center does not extinguish intensity but transforms it. That a world receiving almost nothing from its star can generate something extraordinary from its own reserves. That the quiet edge of a system can be, on its own terms, one of the most violent places in that system. Not because of what it receives from outside, but because of what it carries within. If you could stand on a platform suspended in Neptune's upper atmosphere, which you cannot, because no platform could survive those winds and those pressures and those temperatures, but if you could, what would you experience? You would be hanging in a twilight world. The sun would be a brilliant point of light on the horizon, bright but small, casting a dim illumination that your eyes might eventually adapt to. The sky would be a deep blue fading to black above, with stars visible even during the day because the sunlight is too weak to wash them out. Below you, The atmosphere would descend into darkness and increasing density, the clouds and haze thickening into an opaque murk that hides whatever lies beneath, and the wind would be moving. Not gently, not like a breeze on a summer evening. The wind at your altitude would be carrying you eastward or westward at hundreds of kilometers per hour, relative to the planet's interior rotation. You would not feel it directly, because you and the air around you are all moving together, the way you do not feel the wind when you're inside a moving car with the windows closed. But if you could see a reference point, something fixed relative to the deep interior, you would see it sliding past at a speed that would make the fastest highway traffic on Earth look stationary. And somewhere below you, or at a different latitude, a dark vortex might be forming. An anticyclonic storm, high pressure, rotating slowly, depressing the cloud deck around it, dragging companion clouds of methane ice along its edges. It might persist for a year. It might persist for 5. It might drift toward the equator and die. Or it might reverse course and survive, shedding fragments that briefly become storms of their own. You would not hear it. Sound travels differently in Neptune's atmosphere, and the distances are vast. But the storm would be there, part of the continuous atmospheric violence that this planet sustains in near total darkness, 4.5 billion kilometers from the warmth of the sun. This is the reality of Neptune. Not the serene blue marble of enhanced Voyager 2 images. Not the quiet ice ball of pre-flyby expectations. Not the forgotten world at the edge of the textbook solar system diagram. Neptune is a planet in perpetual atmospheric turmoil, powered from within, changing with the decades, generating and destroying storms of continental scale, sustaining the fastest winds ever measured on any planet, all in a place where the sun is barely more than a bright star in the sky. And it has been doing this for 4.5 billion years. The heat that drives Neptune's atmosphere today is the same heat that was deposited during the planet's formation. It has been leaking out ever since, and it will continue leaking out for billions of years to come. Neptune is not approaching stillness, not on any timescale that matters to anyone who will ever observe it. The engine is running, the atmosphere is moving, the storms are forming and dying and forming again. The wind bands are circulating east and west at speeds that defy intuition for a planet this far from its star. We began tonight by establishing what Neptune should be. A frozen, dim, featureless world at the edge of the solar system, sitting in near darkness, receiving almost nothing from the sun, and therefore doing almost nothing in response. That was the expectation. That was what the physics of distance and diminishing energy predicted. We then saw what Neptune actually is. A planet with the most powerful atmospheric winds in the solar system. A planet that generates Earth-sized storms and destroys them within years, only to generate new ones. A planet whose internal heat, left over from its formation, dominates its energy budget and drives a global atmospheric circulation that has been operating continuously since the solar system was young. A planet whose cloud cover responds to the sun's 11-year activity cycle through photochemistry, proving that even a faint star can reach across billions of kilometers and leave its fingerprint on a distant world's weather. A planet whose true color is not the dramatic deep blue of enhanced images, but a muted greenish blue that hides the violence within. Neptune's terror does not come from any single feature. Not the wind speed alone, not the storms alone, not the internal heat alone. It comes from the contradiction between what you expect and what you find. It comes from the gap between the quiet, cold, dim world that distance predicts, and the raging, dynamic, self-powered world that actually exists. It comes from the realization that the edge of the solar system is not where things end. It is where things continue, powered by sources that owe nothing to the sun, operating in conditions that should produce silence, but instead produce fury. There will come a time, perhaps decades from now, perhaps longer, when a spacecraft enters orbit around Neptune and begins to study it the way Cassini studied Saturn. That spacecraft will carry instruments capable of peering through the haze, measuring the composition of the deep atmosphere, tracking storms from close range over years rather than glimpsing them from billions of kilometers away for a few hours. It will map the interior through gravity measurements and magnetic field observations. It will watch the seasons change. It will see things that Voyager 2 could not, and it will answer questions that have remained open since 1989. But even without that mission, even with only what we know today, Neptune has already delivered its most important message. And that message is simple. Distance from the sun does not mean silence. A planet can sit at the farthest reach of its star's influence, where sunlight is a whisper and warmth is almost gone, and still rage, still churn, still blow winds that exceed the speed of sound, still produce storms the size of worlds, still carry in its deep interior the heat of its own birth, and use that heat to drive an atmosphere that has never stopped moving since the day the planet formed. Neptune is not the quiet, frozen edge of the solar system. It is a world still raging in the dark. And it has been raging there, alone, for 4.5 billion years. Not because anyone is watching, not because the sun compels it, but because the heat is still there. The atmosphere is still deep, and the physics of a spinning fluid world do not care how far away the nearest star is. The wind blows, the storms form, the engine turns, and Neptune, the planet that should have been silent, refuses to be quiet. Good night.